Okay, so in this session, we're going to look at the MCAT equations to do with enthalpy. And the way we're going to do that is think about three really common mistakes that people always make on these questions, and just kind of talk about those mistakes so that if you're aware of them, you're less likely to make them. And then at the end, we'll do two example questions for you to have a go at, and I'll go through the answers. So in terms of your boot camping, the equations you need to boot camp in order to do MCAT questions are these three here. Occasionally, for the moles equals mass over MR, instead it might be moles equals CV. Yeah, there'll be some way of finding out the moles of chemical. Usually it's mass over MR. And the equation I'm going to focus on in this first bit is this first one here, heat equals MC delta T. Now, one of the biggest problems, or most common mistakes with this, is that people use the wrong mass for that mass number there. So I just want to get into what mass you need to use for that mass there. So you're going to have a question. The question is going to describe some kind of system. And in that system, there's going to be some chemicals that are reacting. And those chemicals are either going to be exo or endothermic, so that will either increase or decrease the temperature of the surroundings. Now, the surroundings is usually just a beaker of water or something like that. Okay, so just to simplify it, we've got our chemicals and our surroundings. So some questions for you to think about then. Let's say my reaction was exothermic and my chemicals lost 50 joules. So the heat change for my chemicals is minus 50. What must be, assuming we didn't have any heat loss to surroundings, the exact heat change for the surroundings? The chemicals have lost 50, so it's minus 50. What must be exactly the heat change for the surroundings? It must be exactly plus 50. Right? If I give you £10, I am minus 10, you are plus 10. If the chemicals lose 50 joules of heat, they are minus 50, the surroundings are plus 50. So there's a rule here, which I'm describing, which is the heat change of your chemicals and the surroundings is always exactly, if you do the experiment properly, equal and opposite. Okay, so that's going to be really important. So ultimately, what we're going to try and do is find the delta H of our chemicals. Now, in an equation, everything has to be about the same thing. So if I wanted to find my volume, I wouldn't use Tom's height and Sandra's length and Jason's width, would I? I'd use my height and my length and my width. In an equation, everything has to be about the same thing. So for this equation here, as we're trying to find the enthalpy change for the chemicals, we need to use the heat and the moles of the chemicals. So all the numbers involved in this equation are all about the chemicals. Now, to get this moles here, we use this equation. So you do moles equals mass over MR and feed it in there. So as we're trying here to find the moles of the chemicals, in this equation, the moles, the mass, and the MR must be of the chemicals. In an equation, everything has to be talking about the same thing. Okay, so delta H equals heat over moles. So we're trying to find the heat of the chemicals. So in this top equation, you'd be tempted to say, well, surely we're going to do heat equals MC delta T of the chemicals. And it would be nice if we could do that, but we can't, because we're not going to measure the temperature change of the chemicals. What we do is we measure the temperature change of the surroundings. So usually you'd stick a thermometer in a beaker of water. So the thermometer is not measuring the chemicals that are reacting, It's measuring the liquid that's being heated up, usually. So this equation here, and this is the bit which gets everyone, this equation here is not actually about the chemicals, because we can't find the temperature change of the chemicals, so it's impossible to do that. What we need to make this equation about is the surroundings, the liquid being heated, usually. Okay, so when we're doing our mass here, and this is the thing I'm trying to get at, you need to use the mass not of the chemicals, but of the thing being heated, the surroundings. Okay. So let's look at some actual examples so you can see this in action. There's two main ones you're probably going to come across. One of them to the left here is you're going to have a beaker of water, so this is the surroundings, with a thermometer, and we have some kind of spirit burner or an alcohol burner or some chemicals that are reacting, and they're going to produce some kind of flame or something like that, and it's going to heat up the liquid. So that's our scenario one. So let's just think about that now. Let's go back to these equations. If I'm trying to find my mass here, have a little think, bearing in mind the density of water is 1 gram per centimetre cubed. So if you've got 100 centimetres cubed of water, you've got 100 grams of water. So bearing that in mind, have a little think. For this scenario, what would be the mass we would use in this equation? If you need more time to think, and you're watching this as a video, just pause the video and stop, and then unpause it when you're ready. So the mass would be 100, because the thing being heated, the surroundings, is just the water, isn't it? So it's just 100 centimetres. We wouldn't be using 5 grams, because that's the chemicals. That's what's being burned. This would be the mass we use there. The 100 is what we would use there, because that's the thing being heated. Let's look at a different example. So now I've got 100 centimetres cubed of water, and I'm going to dump into that water 5 grams of chemical, which are going to react in the solution and either be exo or endothermic, and we're going to measure the temperature change. So what would be the mass we use there then in this case? Again, if you need to pause the video to think, just pause it as long as you need, if you're watching it as a video. Okay, it's going to be 105 grams, because the thing being heated is this solution. We started with 100 grams of water, and you added 5 grams to the solution. So that is the chemical, that's what's reacting, but it is now also being heated because it is now part of that solution. So in this left-hand example, our mass that we'd use in heat equals mc delta T is 100 grams, because the chemical is not being added to the solution. On this side here, the mass that we'd use is 105 grams. But notice, it's definitely not 5 grams. The common mistake everybody makes is people go, oh, mass, right, I need to find a mass. Oh, look, that's a mass, 5 grams, there we go, 5. It's like, no, that's the mass of the chemicals. We need the mass of the surroundings. Okay, so that's what we're going to do. We're going to do heat equals mc delta T to find our heat of the surroundings. But down here, we don't want the heat of the surroundings, we want the heat of the chemicals. Let's go back to that first rule we talked about. The heat of the chemicals or heat change of the chemicals, will always be exactly equal and opposite to that of the surroundings. So I'm going to change this equation and put a little minus there. Whatever your heat is here, flip the sign of it there. So if your heat comes out as plus 20, When you feed it into this equation, make it minus 20. If your heat comes out as minus 50, make it plus 50. Plus 7, minus 7. Yeah, so you're just reversing the sign. You're flipping the sign in this equation because you're going from your surroundings to your chemicals, and they're always equal and opposite. Okay, so that's the first common mistake. That's like probably the biggest one. There's two more. I think what I'll let you do is have a try at a question now, and we'll see if you make any of those two mistakes, and that could actually be quite informative. And then I'll go through what those other two common mistakes are as I go through the question. So using these equations then, oh, I should say as well, whenever you get a question, the first thing to do is to think about which of these two situations do you have. Is the chemical separate to the surroundings, so don't add them, or is the chemical being added to the surroundings, so it's becoming like a mixture, a solution, to add them? So that's the first thing to do. So here's a question. Again, if you're watching this as a video, pause the video and then just press play when you've got your answer and you're happy with it, and then I'll go through the answer. Hello, welcome back. So what scenario do we have here? Well, it says the anhydrous copper sulfate was added to the water. So in my scenario, it's this second scenario, isn't it? It's this one here. We've added the chemical to the solution. So I'm going to do heat equals mc delta T. My mass is going to be 100 grams of water and 5 grams of the anhydrous copper sulfate. C, the specific heat capacity, you can get that on your data sheet. It's 4, I would just try and memorize it's 4.18. It's always going to be 4.18. Unless it specifically says otherwise, it's going to be 4.18. And you can find that on your data sheet if you forget. And then our temperature change is minus 3. It's gone down, hasn't it? It's gone 25 to 22. So it's not 3, it's minus 3. So that gives me minus 1316.7 joules. And it's important to remember is that in heat equals mc delta T, this squirts out your answer in joules. That's the second most common mistake. People forget that this squirts the answer out in joules, but you're going to be expected to give your answer in kilojoules. So at some point, you're going to need to divide that by 1,000. You can either do it now, or you can do it at the end, whatever you want. I'm going to do it at the end. Step 2, we're going to find our moles of chemical. So that's going to be mass over MR. Our mass was 5 grams. Our MR is 63.5 plus 32.1 plus 64. Bang that in a calculator. And you'll get that. Notice I'm not going to round yet. We only round at the end of the question, otherwise you could get a rounding error. And then finally, we're going to do delta H equals flip the sign of the heat over the moles. So my heat was minus 1316.7 joules. So I'm going to change that to plus 1316.7 over the moles. Bang that in a calculator, and that comes to 39,564, and that will be joules. Remember, this is in joules per mole. Joules on the top, moles on the bottom, joules per mole. But remember, second most common mistake, forgetting to convert that into kilojoules per mole. So divide by 1,000 basically. So 39, and I'm going to round it to 3 significant figures because that's what the question goes to. We should always, if you look at the question, we should always round what the question does. So that'll be 39.6 kilojoules per mole. Okay. The third most common mistake, whilst we're going through it, is forgetting to flip the sign. So the 3 most common mistakes are getting the wrong mass there, forgetting to flip the sign, and then forgetting to divide by 1,000 to get in kilojoules. Now, if you when you do these questions, you notice you keep on forgetting to flip the sign, a really good safety net that you can do is at the end of your question, once you've got your answer, you can double check whether you've got the correct sign by going back to the question and looking at the temperature change. So as our temperature change went from 25 to 22, that's a temperature change of -3. So that's endothermic, isn't it? If the temperature drops, that's an endothermic reaction. And a fact you need to know is endothermic reactions have a positive delta H. So look, my answer came out positive, good. That fits the temperature change. If the temperature had have gone up, well, that must have been an exothermic reaction. And exothermic reactions have a negative delta H. So it's like an exam skill, like exam technique skill to get into is once you've got your final answer, check the units, check it's in kilojoules, and then just double check the temperature to see if your sign fits what it is. Okay, so I've got a second question for you to try. Have a crack at this one. Again, if you're watching as a video, you can just pause and unpause when you're ready. Welcome back. So again, in this one, this is a different scenario. So now the propane burner is not being added to the water, it's separate. So we've got something which is much more like this scenario here. Okay. So I'm going to do heat equals mc delta T. So my mass, now I'm going to not add the masses, it's just the liquid. So 3 times 10 to the 5, that's a lot of water, times by the specific heat capacity, and then my temperature change was increased by 8, so that's plus 8. That will give me 10,032,000 joules. Remember, this comes out in joules. Next, we can do moles equals mass over MR. Bang in the mass from the question, bang in the MR, get from the periodic table, and that will equal like so. And then finally, delta H, flip the sign of the heat over the moles, so that becomes minus 10,000, so 10,032,000 divided by our moles. Bang that in a calculator and you'll get, 122,613 joules per mole. Again, don't forget the sign. So look, I've got so caught up in writing down my answer, I forgot to carry on that minus sign. That would have lost me a mark, wouldn't it? Well, I'm telling you, it would have lost you a mark. So I need to do my safety checks. Right, okay, let's check. Do I have the right sign? Well, my temperature is increased, so it must be exothermic, so it must be negative. Right, I need to remember the negative. And then units, it's still in joules per mole, so I've got to remember to divide by 1,000, so to 3 sig figs minus 123 kilojoules per mole. Okay, so I bet you my left and right arm in the exam, if you lose marks on this, it's going to be for one of these 3 mistakes. This is what you're going to do. You're either going to use the wrong mass here, you're going to not get the right sign, or you're going to forget to divide by 1,000. So they're the 3 things which, if you kind of like, whenever you do a question on this, if you say to yourself, like actively say to yourself, don't forget those 3 things, then you're not going to do them. So it's just 3 things to remember moving forward. Thank you very much.